All right, so today we're going to be looking at KSP. This looks at how soluble different ionic salts are overall. So the KSP is the solubility product constant. So it looks at how soluble substances are. So it's going to show the dissolution of insoluble ionic salts. So those salts that, according to our solubility rules, would be a solid. Remember, some of them will still become ions, but it's a very small amount. So we're going to look at that insoluble ionic salt, how much of it splits up into the ions. So, for example, the magnesium fluoride. So fluorides tend to be insoluble. So this would split into magnesium ions and 2 fluoride ions. And this is going to be a reaction at equilibrium overall. Because if some of the salt becomes ions, there's too many ions, some of the ions will revert back into the solid salt. So this is going to be kind of a cycle that occurs. Let's look at another equation of the dissolution of ions. So here, if we have calcium phosphate, which is a solid, calcium phosphate will produce 3 calcium ions and 2 phosphate ions. Yet again, in that system of equilibrium. All right, so looking at what KSP actually is, and this is going to be set up the same way that we have done K in previous lessons. But that K value, a larger K value means that the salt is comparatively more soluble than a substance with a smaller K value. All of these are still going to have exponents to the negative power, so they are going to be less than 1. But values that are closer to 1 are going to be more soluble than something that is further away from 1. So the smaller value means that the salt is less soluble. And KSP values are typically going to be given to you. There's a table of them in chapter 16 and appendix 2 of your textbook. These you're either going to be solving for, or they will be given in terms of problems that we're going to do. So here's kind of a sample where you can see the different KSP values. Whereas something like barium fluoride with a KSP of 2.45 times 10 to the -5 is going to be much more soluble than barium sulfate with a KSP value of 1.07 times 10 to the -10. That will be more soluble than something like the copper 2 sulfide, which has a KSP of 1.27 times 10 to the -36. So you'll notice that these all have varying degrees of solubility. But yet again, the lower that exponent is, the closer that number is to 1, the more soluble that salt is when compared to something with a higher exponent value. So some terminology to make sure that you're aware of. Because we will be looking at the solubility as a whole and then the molar solubility of a substance. So solubility in general looks at the grams of solute per liter of saturated solution that can be dissolved. So grams per liter, whereas molar solubility looks at the moles of solute per liter of saturated solution. So one is just measuring in grams, how many grams can dissolve. The other is measuring how many moles can dissolve at that given volume. So here is an example of how we would be finding molar solubility. So here we have a reaction of the lead-2 iodide would split into lead-2 ions into iodide ions. And they have a KSP value of 9.8 times 10 to the negative 9th. This means that at equilibrium, some of the lead-2 has dissolved, but much of it is still a solid that's undissolved. So inside our beaker, we would have mostly the solid, but then some of the ions that are produced. And at equilibrium, the molarity of each ion that's produced in the solution is going to be equal to 1.3 times 10 to the negative third molar. That is because there are 3 ions that are produced. So it's that KSP reverts into those 3 ions. So it does split apart, and this is what we're going to actually have to measure overall. So that number, the molarity of each ion, is referred to as the molar solubility of lead-2 iodide. So you'll note that each ion is that 1.3 times 10 to the negative third molar concentration. So at equilibrium, and this we've done with our solution stoichiometry before, at equilibrium, since there's one lead ion, it has a molarity of 1.3 times 10 to the negative third molar. Whereas since there are 2 iodide ions, those add together to equal a molarity of 2.6 times 10 to the negative third. So since there's twice as many iodide ions, that has twice the molarity. So how we actually calculate this is still using the ICE tables that we've been using. So it tells us that the molar solubility of lead-2 fluoride is 2.15 times 10 to the negative third molar, and it wants us to calculate KSP. So like I say, KSP is just another form of K. So we will be using the same formula of K that we've been using with the products over the reactants. Here, we have to write out our equilibrium equation, just like we did at the beginning. So we have the insoluble salt, we have lead-2 fluoride. That should split into our lead-2 ion and 2 fluoride ions. We have to do an ICE table to figure this out. So I'm going to set up our ICE table. Remember, with equilibrium, solids don't do anything. So we can kind of ignore that column. Since we're starting off with a solid, we have none of the ions initially. And molar solubility is our X factor that we've used in other ICE tables. So that molar solubility value is our X factor that we've used in previous ICE table problems. So that is going to go into our change step, just like we've had before. So we have to add the X value for lead, the 2.15 times 10 to the negative third. For fluorine, though, remember in the C step and the change step, coefficients matter. So we have 2 times that X factor, the 2.15 times 10 to the negative third. That means that our equilibrium concentrations for lead will be 2.15 times 10 to the negative third. For fluorine, it's going to be 4.30 times 10 to the negative third. And those are molarities for both. So those are our equilibrium amounts for the two ions. But it wants KSP. So for our K equation, it is products of a reactant. So we have the lead 2 ion with no exponent multiplied by the fluoride ion squared. And since our only reactant is a solid, remember solids, pure liquids, and don't show up in our equilibrium constant equations. So that is our formula for KSP. So we can plug in those known values. So 2.15 times 10 to the negative third multiplied by 4.30 times 10 to the negative third squared. And when we put that in the calculator, we get that the KSP is going to be equal to 3.98 times 10 to the negative 8th. And yet again, K does not have a unit. So this is one way that it will give you a problem, is it will give you that molar solubility and ask you for the KSP value. All right, so here's another way that you're going to see KSP problems. Here, it wants us to find that solubility. So we have to find molar solubility, which is our X factor, but it wants us to find solubility in grams per liter when given KSP. So we're given the K value and we're trying to figure out what that X factor is. So we have to set this up the same way. We need to write out our equation. So we're looking at the solubility of iron 3 hydroxide. So that will split into the iron 3 ion and 3 hydroxide ions. So setting up our ice table, remember that there's no solid that's going to go in our ice table, so we can ignore that column. For iron and hydroxide, remember, since we are starting off as a solid, both of these are 0 initially. Iron is going to increase by a factor of X. Hydroxide will increase by a factor of 3X. So our equilibrium concentrations for iron 3 is going to be X, and for the hydroxide is going to be 3X. So we can plug that into our KSP equation. So we said KSP is our products. We're going to have Fe positive 3 times OH cubed. So whenever we put this in and plug in our values, we have KSP was 2.79 times 10 to the negative 39th. We said Fe was X and OH was 3X. And don't forget that will end up being cubed. So whenever we kind of simplify this, remember the cube is going to go to not only the X, but the 3 as well. So we're going to end up with X times 3 cubed is 27. And then X cubed. So we end up that the 2.79 times 10 to the negative 39th is equal to 27x to the 4th power. So we have to divide by 27. And in your calculator under math, you can do the 4th root. And we get that x is going to be equal to 1.01 times 10 to the negative 10th. That is our molar solubility, which is moles per liter. The question is asking us for the solubility in grams per liter. So we are going to have to convert from moles to grams. So we can set this up one little stoichiometry step, and 1 mole of the iron 3 hydroxide is 106.874, if I'm reading that correctly, grams. So when we multiply that, that's going to give us the solubility of 1.08 times 10 to the negative 8 grams per liter. So that's the solubility instead of the molar solubility. But molar solubility is whenever you find that X factor, just like you would any other problem. All right, let's do one more problem for good measure. Here it tells us that the solubility of lithium carbonate is 5.48 grams per liter. And what is the KSP? So notice this one gave us the solubility in grams per liter, but in our ice tables, we have to have molarity. So we're going to have to change this into moles per liter. So we can do that first before we plug anything else in. So if we have 5.48 grams per liter, changing into moles per liter, grams would go on the bottom, mole would go on top. The molar mass for lithium carbonate, which make sure that you have your formula correct. So remember, lithium is a positive 1, carbonate is -2, so it would be Li2CO3. That is going to have a mass of 73.89 grams per mole. So that gives us a molar solubility of 0.074 moles per liter. So that, remember, is our change factor, that X factor that we have. So when we write this out as an ice table, so we have lithium carbonate, which is a solid, is at equilibrium with the ions. So 2 lithium ions, excuse me, that's a +1, and a carbonate ion that has a -2 charge. So yet again, we start off with 0 of our ions. Solids we kind of ignore. For lithium, this is going to increase twice as much as carbonate. So remember, our coefficients matter. So it's going to be 2 times that molar solubility, the 0.074, whereas carbonate will just increase by 0.074. So lithium's equilibrium concentration will be 0.148, whereas carbonate is going to be 0.074. Excuse me, I miswrote that up above. So to find KSP, remember, it's going to be our product. So we're going to have the lithium squared times carbonate. When we plug that in, we have 0.148 squared times 0.074. We get that the KSP value is equal to 1.62 times 10 to the -3rd. So this, because lithium is a group 1 salt, tends to be fairly soluble. So that's one that typically we would say would be soluble based on it being lithium.